system and all, right? Newton in heating, Newton in cooling and all. Can anyone briefly say it? Say it. What is lumped parameter system? What is Newton in heating? What is Newton in cooling? Students? What is a lumped system? All of you are there or not? Simply switched on and went off. Manoj Kumar, Saravana Saktivel, Muthukumaran. All of you are there? Manoj
Yes.
Kumar.
So it's the method used for the analysis of transient heat transfer system.
Okay. What is lumped parameter system or lumped system? What is Newton in heating? What is Newton in cooling? What year you did some problems and all? No one knows it. Huh? Vishwapriyan, Aditya, Harikrishnan, Kartikeya, Ritvik. What is lumped system? All of you are there or not? Hello?
Yes, sir. Yes.
Only one or two they are saying. Shall I give marks for assignment marks for only those who answer my questions? Ramkushan, Achudan or Adityan? Huh? Jeffrey, Jetani, Omarish, Joel Dixon. What is lumped system? Jetani, Omarish, Joel Dixon, please switch on your cameras. Omarish, Jetani.
Yes, sir. 1 second, sir.
Jetani, Omarish, are you there? See, if your attitude is like this, then it's very difficult. And most probably in March, you have to come to campus and most probably you will be attending classes there. Let me see how many of you are attending regularly. Okay, ma, what is the difference? What is lumped system? Anyone?
So uniform temperature constant.
Time uniform.
Time uniform.
Temperature.
It's like same variables of something which dependent on the time alone. So like the function is for the time alone.
Okay.
Like that. As far as I know, I told you.
See, a solid which is introduced into your new zone, right? New temperature zone, whereas the internal resistance of the solid is almost negligible when compared to the convective resistance. Okay, or surface conductance. Some textbooks they used to say surface conductance. Okay, so the internal resistance offered by the solid, okay, or internal conductive resistance is almost negligible when compared to the surface conductance. Okay, so if your body is small and if it is dropped into an environment where you have a very high temperature or very low temperature, so that what happens is within few minutes the temperature of the whole solid equals to the temperature of the surrounding fluid. Okay, so that is usually that type of system is assumed to be lumped system, and that type of heating process is said to be Newtonian heating, or the type of cooling is said to be Newtonian cooling. Okay, so the process in which the internal resistance of a solid or a body is almost negligible when compared to the convective resistance, then it is said to be a lumped system. Okay, for lumped system, the combination of these two, that is the Bayard number will be, where Bayard number is equal to HL by K. Bayard number is less than 0.1, then we used to assume it as a lumped system. Okay, when it is 0.1 to 100, greater than 0.1 to 100, then we used to assume it as infinite solid. When it is tends to infinity, then we assume it as what's that, semi-infinite solid. Okay, so lumped system, internal resistance is almost zero when compared, or negligible when compared to the convective resistance. Okay, or Bayard number less than 0.1 means lumped system. Okay, greater than 0.1 and less than 100 means then it is infinite solid. Okay, now you may ask a question. Yeah, this is the characteristic length volume by surface area. Okay, and when using lumped parameter system, we will be using LC equal to L, plane wall thickness, that is the thickness divided by 2, and for cylinder it is radius divided by 2, where R naught is nothing but the radius, and for sphere it is R naught divided by 3. And we also discussed about the time constant, which is nothing but tau t. Okay, and yesterday I had told you about sensitivity of the measuring instrument, and similarly response time of the measuring instrument we have discussed. Okay, and there are two numbers, one is Bayard number and the other one is Fourier number. Okay, the Fourier number, again, the product of Bayard number and Fourier number is very important. Okay, Fourier number is given by alpha t divided by LC squared. Okay, and we did some problems also on this. Okay, and Fourier number, when we talk about Fourier number, okay, Fourier number is again a dimensionless number or a dimensionless time, which is given by alpha t by LC squared. Okay, alpha t by LC squared, where alpha is nothing but diffusivity, t is nothing but time, and L suffix c is nothing but the characteristic length, which varies for different solids. Okay, and what happens is, the as it was mentioned here, the Fourier number at time t can be viewed as the ratio of rate of heat conducted to the rate of heat stored at that time. Okay, Q conducted divided by Q stored. Okay, so Fourier number roughly it is mentioned as rate of heat conducted divided by rate of heat stored in a given solid. Okay, now when we have a very large plane wall, okay, having thickness L or radius R naught, and sphere similarly radius R naught. Now when we assume lumped system is Bayard number is less than 0.1, but what happens is, in some cases the conductive resistance is almost equal to the convective resistance. Okay, in that case the Bayard number will be equal greater than 0.1, or sometimes it will be equal to 1 also. Okay, so assume that you have a body like this. Assume that you have a body like this. Students, one more thing. Today evening also we are meeting. Am I correct?
Yes, sir.
At 6 p.m.
Yes, sir.
Yes, sir.
Yes, sir.
All the 66 students. Anyway, I will put this in the WhatsApp group also. Suppose, see, assume that you have a infinite solid. Okay, which will be having infinite length in the other two axes. Okay, assume that you have infinite length along the y-axis and similarly infinite length along the z-axis. Okay, so like this it goes on like this. So so it's if y-axis and z-axis is not finite, it's not defined, only the x-axis having certain length. Okay, then usually that particular solid is said to be infinite solid. And for infinite solid, okay, so infinite solid is nothing but the solid which extends infinitely in the other two directions apart from x-axis. Okay, so in case of infinite solid, we will be having Bayard number greater than 0.1. Okay, and Bayard number will be less than 100. Okay, so in this case Bayard number equal to HL by K, or we know that L by Ka divided by 1 by HA. Okay, so that is the usual definition. Or in this case, what happens is the surface that is conductive resistance. Okay, conductive resistance will be almost equal to, approximately equal to convective resistance. All of you are able to understand this, students? Students, when we describe a solid as a infinite solid, the convective resistance is approximately equal to the conductive resistance, or L by Ka. See, when the Bayard number will be greater than 0.1 or when it will be equal to 1. Okay, so when this L by Ka and 1 by Ha values were equal to each other or almost similar, then you will be having Bayes number equal to 1 or greater than 0.1. Am I correct? Am I correct,
Yes, sir.
students? All of you are
Yes,
able
sir.
to understand this?
Yes, sir.
I don't know whether you
Yes,
are
sir.
able to understand or not. See, yeah, infinite solid is the one which extends infinitely in the other two directions, especially y-axis and z-axis, apart from x-axis. Okay, so we may take the partition wall in a centralized air conditioning system. The partition wall extends. The thickness of the wall will be lesser. Okay, partition wall in a room, whereas the length and the height will be more. Am I correct or not? Am I
Yes, sir.
correct? The length and height will be more, especially when we take multiplex complex and all, right? We will be having the wall thickness. We know that it will we can measure it, but whereas the length and height, it's almost longer. Okay, so what happens here is in those type of solids or those type of walls in which the heat transfer, we may assume it as those type of solids or those type of walls can be assumed as infinite solid. Okay, so now what happens is here in case of infinite solid, okay, again it depends upon the temperature is a function of the x, okay, the thickness. Okay, so thickness from the center up to any point. Okay, and it also depends upon time, it also depends upon the thermal conductivity, it also depends upon thermal diffusivity, and it also depends upon the convective heat transfer coefficient of the fluid it comes in contact. H is nothing but convective heat transfer coefficient of the fluid, and T infinity is nothing but the surrounding fluid temperature, and Ta is nothing but the initial temperature. Is it fine? Is it fine,
Yes, sir.
students?
Yes, sir.
Okay, so the temperature is a function of all the things. Okay, the wall thickness. If the wall thickness is very lesser, then what happens is the temperature achievement is much more. That is the wall attains the fluid temperature much more easily, right? So, and it also depends upon time, small t, thermal conductivity of the wall or material, thermal diffusivity. I have already told you, thermal diffusivity gives us an idea about the penetration of heating or penetration of cooling, right? I have already told you, right? So that's why Fourier number gives an idea about the penetration of heating or penetration of cooling of a particular body, and H is nothing but the surrounding convective heat transfer coefficient of the fluid with the solid. Okay, and Ti and T infinity were nothing but the initial temperature and surrounding fluid temperature. So the diamond what happens here is here the temperature depends upon you have the dimensionless temperature T at x comma yeah at T minus T infinity divided by Ti minus T infinity. Here T naught is nothing but T naught is not there in this expression. You will be having Ti. Okay, so in some textbooks they used to mention Ti as the initial temperature. Okay, and T is nothing but the temperature at any given instant of time t, and x equal to capital X equal to x by L, the dimensionless distance from the center. Okay, any point small x from the center is yeah, small x, and that particular point divided by the length. Characteristic length is nothing but the thickness divided by 2, so which is given by capital X, and Bayes number we know that HL by K. Fourier number we know that it is equal to alpha T by L squared. Okay, so now what happens here is you have initial condition and you have boundary condition and x equal to 0 and tau greater than 0, and boundary conditions x equal to L and tau greater than 0. So you will be having 2 or 3 different boundary conditions, and for this we will be getting approximate solution. Okay, we will be getting approximate solution. Okay, so getting this approximate solution or one time solution in the form of, see, you will be getting this the solution of one dimensional heat conduction involves infinite series which are difficult to deal with. So what they discussed is they used charts, okay, to find the solution, of a plane wall, cylinder and sphere. What they use is they used 3 charts, okay, which were given by Haisler, right? And these charts were said to be the Haisler charts. The Haisler charts has got the temperature distribution on the y-axis and tau on the x-axis, and the parameters were nothing but 1 by Bayard number or K by HL. Okay. So now you may ask a question, sir, where can I find this? Okay. So in your data book, all students, all of you are listening? All of you are able to see this?
Yes, sir.
Now let me show it. So go to infinite solid in your data book. Go to infinite solid in data book. Let me show it to you. See, anyway, heat and mass transfer data book, those who have not got it, try to buy it. Most probably CAT 2, you will be having offline test, and most probably it will be in campus if everything goes well. Okay, so it's compulsory that you have to have the data book with you. What is the page number for infinite solid, ma? Actually, the scanned copy and all, it's not correct for us to give it to you, but
The
since
72.
you infinite solid 63, page number 63. Yeah. Now you can see here, students, Fourier number greater than 0.1, infinite solid, and you have the thickness. The thickness is the total thickness is 12, or half the thickness is taken as capital L. All of you are able to see this, students? Hello.
Yes, sir. Yes.
Yes, sir.
So in the latest data books that is the page number will be different. Okay, please don't worry about it. Okay, if you have the data book, latest data book, you refer that. Okay, now what happens here is for central plane temperature T0 minus T infinity by Tn minus T infinity. Okay, please refer chart 65. Okay, so the dimensionless portion is x by L, and the central plane temperature T0 minus T infinity by Ti minus T infinity, where now T0 is nothing but the center plane temperature, Ta is nothing but the initial temperature, and T infinity is nothing but the fluid temperature. So this is where you have to be very careful. Okay, in the what's that lumped system? In the lumped system problem, what we have taken is in the lumped system. Yeah, this is a steady state internal heat generation. Yeah, in the lumped system problem, we have taken T0 as the initial temperature. Okay, so please don't get confused. So often students get confused when they calculate the Bayard number. This is valid only for Bayard number when it is less than 0.1, and when the Bayard number is greater than 0.1, then we have to go for this. We have to go for the infinite solid. Okay, and here T0 is nothing but the central line temperature or center plane temperature. Okay, and T0 is referred as initial temperature there. Here it is center plane temperature. Ti is the initial temperature. Okay, so to get that, so you have to refer 65, chart number 65 and 66 for infinite solid, and for long cylinders you have to refer chart number 69 and 70, and for sphere you have to refer chart number 71 and 72. Okay, now so this is chart number. Yeah, is it visible now, students?
Yes, sir.
Yes, sir.
Now you have the T0 minus T infinity divided by Ti minus T infinity. So in case of infinite plane problems, you will be given the surrounding fluid temperature, which is nothing but T infinity, and Ta is nothing but the initial temperature of the solid. Okay, and T0, you will be asked to find out the center plane temperature, and you will be sometimes asked to find out what is the temperature at a distance from the center. All of you are able to understand, students?
Yes, sir.
Only one fellow is saying yes, I don't know. So you have a solid like this, you have a solid, and the temperature at the center is nothing but T0. Okay, and temperature at a certain distance x. Students, all of you are able to understand
sir.
this? This is X.
Yes, sir.
So temperature at this from the center at a certain distance X. Okay. So for this, you will be calculating X by L, where L is nothing but of the thickness of the slab or the wall. Okay. Okay, students.
Yes, sir.
Yes, sir.
So
Understood.
you will be asked to find the central line temperatures or center plane temperature, and you will be asked to find out that is temperature at a distance X from the center. Is it fine? Say yes or no.
Yes,
Yes,
sir.
sir.
Okay, so for that, first temperature at midplane. Okay, so you can use this chart T9 minus T infinity by Ta minus T infinity divided by. So you can easily calculate Bayard number. Bayard number is nothing but HL by K. After calculating Bayard number, you can see here 0.1, 0.2, 0.3, 0.4, etc. And similarly, Fourier number is alpha tau divided by L squared. Okay, you can calculate this. Okay, from this you can calculate what is T naught. Suppose if you are asked to find out what is the the x-axis Bayard number. What about the y-axis? Students, y-axis what it is given? This is X by L. Uh, Students, those who have, because the person scanned here, he has not given this correctly. What is the y-axis, ma? Please tell me from your charts.
So
Those-
T XL minus T infinity.
What is that?
T X by L minus T infinity by T naught minus T infinity.
Okay, so the x-axis is Tx by L. Okay, okay. Yeah. Here it is
Y-axis.
given. I'm sorry. Y-axis. Yeah, that's correct. See, the other one is, the second one is Txl. Yeah, Tx by L minus T infinity by T naught minus T infinity. Refer chart number 66. So the chart number 66 is chart on page number 66. Okay. So here Tx by L minus T infinity divided by T naught minus T infinity. Am I correct?
Yes, sir.
Yes.
Okay. So this is what it was mentioned here. I'm sorry. Yeah, it is mentioned already. Yeah. Tx by L minus T infinity by T naught minus T infinity. So the first one is central plane temperature. The second one is to find temperature at any point. So these two charts were said to be the Haisler charts, ma. Okay. So the Haisler charts were the ones which were used to find out the solution for infinite solids. Is it okay, students? Is it okay?
Okay, sir.
Shall we start do one problem in this infinite solid?
Okay,
sir.
sir.
A solid extends itself infinitely in all directions except one is infinite solid and semi. Yeah, all of you please take your data book, and from the data book for steel, please tell me the values for steel. Okay, so the problem given is a 60 mm thick large steel plate initially at 440 degrees C is suddenly exposed to both sides to an environment with a convective transfer coefficient 235 watt per meter Kelvin and temperature 50 degrees C. So now from this data book we know that T naught is nothing but the center plane temperature and TA is the initial temperature. Okay, so the initial temperature and T infinity is given. Am I correct? Am I
Yes, sir.
correct, student? Ti is the initial temperature. The initial temperature is 440 degrees C. And T infinity, surrounding fluid temperature is 50 degrees C. And H value is 235 watt per meter Kelvin, meter squared Kelvin, I'm sorry. And after time T or tau equal to 4.3 minutes, okay, 4.3 into 60, how much it comes? 60 into 4, 258, Am I correct? Please.
Yes, sir. Yes.
Yes, sir. 250.
258 seconds. Okay. So after 258 second, okay, what is the temperature at mid plane and at a distance 15 mm away from the mid plane? Also calculate the heat energy removed per unit area of the plate during the period. Okay. So first you have to use Haisler's chart. So we have to use the three charts, Aisler's charts. Okay. So let me show it to you. Oh. Yeah, this is for flat plate. Am I right?
Yes, sir.
Hazel's chart. Now, when we decide we have to go for Hazel's chart, first we have to calculate Bayat number. Bayat number is equal to HL by K, and L, which is equal to thickness divided by 2. Am I correct? So 30 mm, 60 by 2. Or some of you may ask, why sir has put on that day directly 30 mm? Because the mentality of the people is you will be studying this everything at the last minute. So 60 by 2. So 0.03 mm, sorry, 0.3 meters. Am I correct?
Yes, sir.
Okay. So HL by K. What is the thermal conductivity of steel? Again, when it is given a steel, immediately you people will blinking. Where
For
is the
this one,
property of materials?
2, sir. Page 2 or 3. Sir,
Uh,
but there's like
which type of
different
steel
kinds
you
of
are
steel.
going to take, ma?
A carbon steel.
Yeah, carbon steel is better. Okay, it will be having better thermal conductivity, I think. Where it is carbon steel? Yeah,
Page
carbon
2.
steel. Yeah, page 2. All of you are able to see this? Rho is 7753, CP is 486, and K is 36.3. All of you are able to see this, ma?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Students? Yeah. So, yeah, now let me take the values. What is the density? Density rho is? Tell me, anyone?
7753, sir.
7753 kg per
Kilogram.
meter cube. And CP?
CP 486, sir. Joule per kilogram.
486 and 36.3. Okay, 486. Students, all of you are able to understand how I am taking all these things? Assuming
Yes,
carbon steel. Okay, so you have to write assuming carbon steel.
So
See,
we
this
can
particular,
assume any steel, sir.
yeah, you can assume. That is your duty, ma. You are the mechanical engineer. You are going to design. Rho K. What is the K value, ma?
36.3, sir.
So most probably I will give you. See, if I don't give you, then you have to assume. Okay. So you have to assume, and according to that particular problem, you have to do the calculation. Now, what is this for this? Now, Bayat number, calculate Bayat number faster. We are running out of time.
0.19, sir.
How much?
0.194.
What is H? What is L, ma?
H is 235 given, no, sir.
235 into
0.03
0.03 divided by
divided by
K value,
36.3.
36.3. How much it is?
0.1942.
1942. It is greater than 0.1. Okay. So since it is greater than 0.1, we can use assume infinite solid. Okay. See, all these things I will be expecting from your answer sheet. Okay. If you don't find out Bayat number, I don't give you mark. Okay. Assuming infinite solid. Suppose if you assume a lumped system and if you find the solution, you won't get full marks, or you won't, if your assumption is wrong, then you will be losing all the marks. Okay, please understand that also. What is the page number? Yeah, it comes after lumped system. Yeah, so this is the chart, right? This is the chart. Is it visible to you all?
yes, sir.
Yes,
T
sir.
naught minus T infinity by, so you are expected to find out. So this is the chart. Okay, T naught minus T infinity by Ti minus T infinity. And here the x-axis is, what is the x-axis? alpha tau by L squared, right? Alpha tau by L squared. Okay. And similarly, the curve is
Yes, sir.
HL by K. The curve
Yes, sir.
is, yeah, yeah, I will come to that. Now, what is alpha? We have to check alpha. What is the alpha value? Whether it is given in page number 2. You have to take alpha value also. Thermal diffusivity it is given, right?
9.7 into 10 power minus
For carbon steel, it is 9.7 into
9.7
10 power
10 power
minus
minus
6.
6.
Okay. So alpha values also you have to take. How much? Please tell me the value, ma.
So
9.7 into 10 power minus
6.
6.
Into 10 power minus 6. Now alpha tau by L squared. So 9.7 into 10 power minus 6 divided into tau. What is the time seconds mark given in the problem? After 4.3 minutes. How much seconds? 258 seconds.
258. Sir.
So 258 divided by L squared. What is L? Characteristic length 0.03 meters. Okay. So 0.03 the whole squared. So what is the alpha tau by L squared value? Please, Biot number we have got HL by K is 0.129. Sorry, 1942. So approximately 0.2. So this value, this you can look into the curve 0.2. The first curve is 0.1, I think. Second curve is 0.2. Now
So
calculate what is all.
0.027.
Huh?
0.0278.
0. Which comes 0.0278.
78.
So approximately 0.03. Am I correct?
Yes, sir.
Okay. So approximately 0.03. And you can look into here.
Sir, I'm getting 2.7, sir.
Just 2.78.
Yes, sir. 2.78, sir.
2.78.
Yes,
Yes,
sir.
sir.
Yes, sir. 4A number is 2.78, sir.
2.78, sir.
Please check your values.
So 2.78 only we are getting, so.
Okay. No issues. What year?
Oh, yes, sir. Yes. It's 2.7.
Okay. See, this is what happens. Okay. Instead of looking into 2.78 or 3. Okay. So that is you can look there 2.78 or approximately 3. Now, this is the first chart. In the first chart, okay, you can see here 0.01 is given HL by K and HX by K is nothing. Oh, see, this is semi-infinite solid. Yeah. HL by K 0.1, 0.2 is given. Am I correct? All of you are able to see this?
Yes, sir.
Yes, sir.
Yes, sir.
0.1, 0.2. Is it visible to you? 0.3, 0.4 up to 100?
It's visible, sir.
It's visible, no? Now, what we have got is, we have approximately got Biot number equal to 0.194. That is 0.2. Am I correct? Am I correct or not?
Yes,
Yes,
sir.
Yes, sir.
Yes, sir.
And we have got the Fourier number as 2.78. Now, you have to get the coincidence between the Biot number. So you have to take this one, the second curve, and 2.78, Amma. What
Yes,
is
sir.
Fourier
Yes, sir.
number?
Yes, sir. 2.78,
So
sir.
2.8. Okay, so you can see here 2.5, 2.6, 2.7, 2.8. So this is 2.8 and intersection between this 0.2 and 2.8. So where it comes, you can see here 2.8. So I am getting here somewhere around 0.62.
0.65, sir.
6, sir.
No,
0.65.
it's above 0.6. For me,
0.65, sir.
So
no, it's not 0.65.
2.8, no, sir. You're taking here
2.2.
2.6, sir.
Huh?
2.8, no, sir. You're taking near 2.6. So 2.8
See, this is
would
3.
be. Yes,
This
sir.
is 3. Okay. 2.6, 2.7, na?
2.78, no, sir. But
7, 8, sir.
2.8.
Yeah,
look here.
take
So
0.8.
approximately 2.8, ma.
Yes, sir.
So it is approximately 2.8. So this is 3. I'm moving along the curve 2.9 and 2.8. So it comes above
Sir,
0.6
it'll be
only.
around 0.6, sir.
That's what I told 0.62 because one division is 2, 4, 6, 8. So I told 0.62. For me, it is
Yes,
0.62.
sir. Yes, sir.
Yes,
Okay.
Sir. 562, sir.
Okay. So from this, so you have to find. All of you are able to see how I got this value 0.62.
Yes, sir.
Yes, sir.
Everyone?
Yes, sir.
Okay. Now from this, you can easily find out. Now you can find out what is the temperature. Already the time is so now T naught minus T infinity by Ti minus T infinity is equal to 0.62, or some of your friends said 0.6. Now substituting the value T naught minus what is the initial temperature and surrounding fluid temperature 440 and 50 degrees. Am I correct?
Yes, sir.
So what is T naught? (390 into 0.6 plus 50). Central line temperature.
284.
284, sir.
284 degrees C. Okay. Now you have found one thing. The second thing is you have to refer the second chart. X by L. Right? So Tx by L minus T infinity divided by Ti minus T infinity. Yeah. What is the other question asked? 15 mm away from the midplane. Okay. So what is the total thickness? The total thickness is 60. From the center line, it is 30. Now, 15 mm away from the center line. Ma. Second question is, so this is the center line. So at center line x equal to 0. So from the center 15 mm. Okay. All of you are able to understand?
Yes, sir.
Yes, sir.
The total is 30. Okay. Thickness divided by 2 is 30. 15 mm away from the center. So x by L, which is equal to 15 by 30. So which is nothing but 0.5. Am I correct?
Yes, sir.
Yes, sir.
Okay. Now for this you have to do you have to take the second chart. Okay. So in the second chart, what it is mentioned, the x-axis is Bayard number HL by K, and the other one is x by L. So x by L is 0.5. So this is 0.5. Am I correct? All of you are able to see
Yes, sir.
this or
Yes, sir.
not?
Yes.
See
Sir, we are
0.2,
able to
0.2, 0.4, 0.5 up to 1 it is mentioned. Am I correct? All of you
Yes.
are able to see this?
Yes,
Yes.
sir.
Yes, sir.
Okay. Now from this we know that x-axis. Please tell me the x-axis. What is the sorry, y-axis? Tx by L minus what is the expression, ma?
T infinity, sir. T
Minus
square
T
minus T
infinity
infinity divided by T
divided
naught minus T infinity.
T naught minus T infinity, where T naught is nothing but the initial temperature. Am I correct?
Yes, sir.
Yes,
So
sir.
this we have to get from graph. From graph. Okay. So x by L is 0.5 and HL by K is what is HL by K? 0.2. Am I correct?
Yes, sir.
Bayard number.
Yes, sir. Yes, sir.
So from the graph, find this. This is the x-axis, sorry, y-axis. X-axis is Bayard number, and these were the curves which nothing but x by L. So here x by L equal to 0.5 for our problem. So take the 0.5 curve. and get the intersection. And after getting the intersection, find out the y-axis. Now, all of you please check 0.5. So
close
this
to
is 0.5.
0.3.
And SL by K, how much we got, ma? 0.2.
Yes, sir.
What is Bayard number?
0.2, sir.
0.2. 0.2, get the intersection point between 0.2 and 0.5. So this is the 0.5 curve. And 0.2, approximately it comes around 0.96 or 0.97. Am I
0.98.
correct?
Yes, sir.
0.98. Okay.
0.98, sir.
0.98. Some of your friends say the y-axis value is the y-axis value. This expression is Tx by L minus T infinity by T naught minus T infinity equal to 0.98. Okay, so now Tx by L, which is equal to T infinity plus 0.98 into T naught minus T infinity. How much it comes?
432.2.
T infinity is 50 degrees. 0.98 into 440 minus 50.
432.2, sir.
432.2 degrees C.
Sir, T naught is 200 something, 284, sir. It's the central line temperature.
Is it so?
I think so.
Yeah, T naught. That's very good answer, ma. T naught is central line temperature, not initial temperature. I'm sorry, ma. Yeah, what he said is right. T naught is central line temperature. Okay, central line temperature. How much we found? 284. Substitute 284 here, ma. Correct. That's correct. 284 here. That's correct. So this is where we do mistake. How much it is now? 284.
279.32, sir.
279.
Yes, sir.
It will be greater, ma.
Oh, 384, sir. Okay, sir.
284 minus 50.
No, sir, it's 279 only.
279 only. Okay, fine. 279 degrees C.
0.32, sir.
Okay, ma. 279 degrees C. Let's accept this.
Yeah,
So,
okay, sir.
okay. Now we have T naught. So in this expression, we have to substitute T naught. Whereas here, we have to substitute Ti. Ti is nothing but initial temperature 440. And we got T naught. After getting T naught, we have to find out Tx by L. So Tx by L is 279. Okay. So the central line temperature is 284 and sorry, it's not the central line temperature. T naught is the outer temperature, I think. No, it's center plane temperature only. Okay. So center plane temperature T naught is we have got this answer. And finally, there is one more thing which is asked in the question. What is the other thing which is asked in the question? Total energy removed per unit area of the plate. How to calculate it? Total energy removed per unit area. So we have calculated the temperatures. How to calculate the total heat energy removed per unit area? Again, you have to go back to the chart on page number 67. Okay. So small q is nothing but instantaneous heat flow at the surface, HA del T. Capital Q by Q naught, you have to find out. Q naught is nothing but the heat capacity of the body above T infinity. Okay. And Q naught equal to rho CL into Ti minus T infinity, where C is nothing but specific capacity, rho is nothing but density, and L is nothing but the significant length, which is nothing but thickness divided by 2. Ti we know that, T infinity we know that. Okay, so we can find out what is Q naught, which is nothing but the heat capacity, but the heat flow, right? We have to refer the chart again on page number 67. So you have to refer after finding out Q naught, you get Q naught first and go to the graph on chart page number 67. This chart, okay. So from this chart, you have to get Q by Q naught value. So this is Q by Q naught. Y-axis is Q by Q naught. X-axis is at H squared alpha tau by K squared, or Bayes number squared into Fourier number, and this is Bayes number. Okay, so from this graph, we have to calculate. From this graph, we have to calculate. Is it fine? The y-axis is Q by Q naught. Students,
Yes,
students,
sir.
is it
Yes.
visible?
Yes, sir.
The y-axis is Q by Q naught, and x-axis H squared alpha tau by K squared, or Bayes number square into Fourier number, and this is the Bayes number. Okay, we have already calculated the Bayes number. It comes around 0.2, and we have to calculate this H squared alpha tau by K squared, or Bayes number square into Fourier number, and after getting that, you have to find out Q by Q naught, and from that you have to find out Q. Q naught, already we have the formula rho CL divided by, sorry, rho CL into Ti minus T infinity. After getting Q naught, you have to find out Q. So this particular thing, the heat energy removed, I will be doing it in the evening. Is it fine?
Fine, sir.
Yes, sir.
Okay.
Students,